Good afternoon, Valmiki. Good afternoon. So, very good afternoon to all of you. So, let's go ahead with the alcohols, phenols, and ethers. So, as you all know that yesterday we have completed the ethers preparation and the physical properties, right? So, we have already completed the alcohols and phenols part, and yesterday we have started with the ethers, and we have studied two preparation of ethers, right? So let me just recall the two preparation and then let's move on to the chemical properties of ethers in today's class, okay? So here is the two preparation. First one is by dehydration of alcohol, okay? And second is Williamson ether synthesis. So in dehydration of alcohol, we took a primary alcohol and used some dehydrating agents, and that undergoes dehydration and they led to the formation of ether. Okay. And coming to Williamson synthesis, the mechanism is we have to take an alkyl halide and it has to be treated with alkoxide, okay, sodium alkoxide or some other alkoxide, and they follow SN2 mechanism to form the ether. Okay. So these are the two methods of preparation we have studied in yesterday's session. All right. So, and after that, some informations about the physical properties we have done. Okay. Like we have done the boiling point and the solubility criteria of the ethers yesterday in physical property. So now moving ahead with the today's topic. So the learning objective for today's session is chemical properties of ethers. Okay, so this is the last topic of this lesson. So let's go ahead with the chemical reactions of ethers. All right. So initially we are going to study about the carbon oxygen bond cleavage. Okay, we all know that the formula for ether is, general formula for ether is ROR. So you all know that we have carbon oxygen. If R is CH3, then we will have CH3OCH3, right? So we have carbon oxygen bond, two carbon oxygen bond. So first of all, we are going to study some reactions in which the carbon oxygen bond in ether is going to get cleaved. Okay. So the cleavage of carbon oxygen bonds in ethers is the topic. Now moving ahead, ethers are less reactive, so the cleavage of carbon-oxygen bond in ethers takes place under drastic condition with excess of hydrogen halide. So what they are trying to say, listen, the carbon-oxygen bond cannot be cleaved easily. It is less reactive. So we cannot do the reaction at a normal condition. We have to use some drastic condition. Drastic means at some high temperature and high pressure we have to use. Okay, using excess of hydrogen halide. HX, hydrogen halide means HX. Okay, so let's see the reaction. Let me take an ether, okay, and let me treat it with HX. HX is the hydrogen halide. So now what will happen, the carbon-oxygen bond will break. Okay, so now here this bond is going to be broken down and it leads to the formation of alcohol, and R dash X is the second byproduct. Got it? So now you may ask me, ma'am, we have two carbon oxygen bond because both of them are alkyl groups, right? So both are carbon oxygen bonds only. Which carbon oxygen will break? What is the criteria for it? Or any bond can break, or is there any condition for this particular bond to be broken down or not? Okay, I will give you the reason. So if the two R groups are same, then there is no issue. If the two alkyl groups are different means one will be bigger in size compared to the other, right? So here I have taken the case in which the R group is bigger in size compared to R dash group. For example, R can be C2H5 and R dash can be CH3. Okay, C2H5 size will be bigger than CH3, right? So if this is the case, then the halide will combine with the smaller alkyl group. Halide will combine with the smaller alkyl group. So since R dash is smaller here, so X is the halogen, right? The halide part will go with R dash. Okay, clear for all of you? Suppose if I have C2H5 OCH3, and if I try to treat this with HCl, so what will happen? Since CH3 is the smaller alkyl group, so this bond will break and CH3 will go out with Cl, and it leads to the formation of C2H5 OH and CH3Cl. Are you getting my point? So this is the thing. So here we are getting an alcohol, and that alcohol will again react with another mole of HX. It will react with one more mole of HX, and it will lead to the formation of one more alkyl halide and water. Okay, because we have one more CO bond, right? So that will break, and this H2O will go out, and we will get RX. Clear? So we have to do this reaction of ether with excess of hydrogen halide, excess of HX. Okay, so that both the CO bond gets cleaved and leads to the formation of alcohol and aldehyde in the first step, and alkyl halide and water in the second step. Clear for all of you? So this is how the cleavage of CO bond occurs and the reaction takes place. Okay. So do you have any doubt from this? Shall we go for the next reaction? Shall we go for the next reaction? Okay. Jabrun Sultana, I'm seeing you after a long gap. Huh? Okay. Okay, fine. So let's go ahead with the next reaction. So the next reaction is the reaction with HX only. But here we are going to take an aromatic ether instead of aliphatic ether. Okay, so I have taken an alkyl aryl ether, which is an aromatic ether, and it is reacting with HX, and it leads to the formation of phenol and RX. So alkyl aryl ethers are also having two carbon-oxygen bond, but the cleavage, the breaking occurs, the breakage of bond occurs only at this part. Okay, this particular carbon-oxygen bond will not be broken down. It is due to the more stable aryl oxygen bond. Due to the more stable aryl means the aromatic part. So this aryl oxygen bond is more stable. Okay, so that carbon oxygen cannot be broken down, and only the other one to which the oxygen is attached to alkyl group will be cleaved, and it will form the product. Okay, and it is giving this bond is breaking, and we are getting RX, and the H is going and getting attached to the oxygen. So we get a phenol and an alkyl halide. Okay, suppose if I have C6H5 attached to OCH3. So I have two CO bonds, right? And if it is treated with HCl, what will happen? This bond will break. So I will get phenol. One of the product will be phenol, and the other one is CH3Cl. Okay. So what is the reason? The reason is very important. Okay. The reason is the aromatic ring, the aryl oxygen bond is highly stable due to resonance. So the bond will not be broken down. Okay. Clear? So now we will discuss about the reactivity order of HX. Okay, we have different halogens, right? We don't have only chlorine. We have fluorine, we have chlorine, we have bromine, and also we have iodine. So all these four elements are the halogens. So we should know which halogen, which hydrogen halide compound will be more reactive for these reactions. Okay, so let's study the reactivity order of HX towards ether. So let me take HCl first, and the second is HBr, third one is HI. So what do you understand from this? What do you understand from the bond length of these three compounds? Is it increasing or it is decreasing from HCl to HI? Is the bond length increases or decreases? Can anyone let me know? Yeah, very good. Bond length increases on moving down the group, right? So that is what we all have studied. So if the bond length increases, the bond can easily be broken down. Okay. The HI bond will be very weak. So the HI bond can easily be broken down. So it will be more reactive. Okay. It will be more reactive. So the reactivity order will follow the same order of bond length. Okay. HCl is least reactive compared to HBr and it is less reactive compared to HI. Okay. So we don't do reactions basically with HF because the HF bond length is very, very small. Okay. Bond length is very small means bond strength is very high. Okay. The bond, HF bond is very strong. HF bond is very strong. So it cannot be cleaved so easily to undergo such reactions. So it will take time. It will take time. So we don't take HF for the reaction with ether. Okay. So the reactivity order is very, very important for HX towards the ether. So just have a note of it. Now we will move ahead with the next concept. Okay. When one of the alkyl group is a tertiary group, the halide formed is a tertiary halide. This point is very important. We are going to do the same reactions only, but the reactant which I am going to take is going to be different. Okay. So you see here, this is an ether and the name of this ether is 2-methyl-2-methoxypropane. Okay. So this is one R group. This is one alkyl group and this is another alkyl group. So if this is R and this is R dash, R, O, R dash. Okay. So this is an ether. And one among the alkyl group is a tertiary group, right? The first one, first R group is a tertiary group. So if tertiary group is present as one of the alkyl group, then the halide formed is a tertiary halide. Okay, we are getting an alkyl halide at the end, right? If it is treated with the hydrogen halide HX, it will lead to the formation of alcohol and alkyl halide, right? So that alkyl halide part will be the tertiary halide part. Clear? Can you able to understand? So we have two CO bonds. In this CO bond is getting broken down. Okay, so it is getting broken down and we are adding I here and H here. So we get a tertiary halide component as alkyl halide component and the other one will be the alcohol. We are getting a methanol. Okay, CH3OH is the methanol. So why we are getting a tertiary halide component as a halide component? There should be some reason, right? I will give you that. In step 2 of the reaction, actually this reaction takes place in 2 steps, okay? So in the step 2 of the reaction, the departure of leaving group, which is CH3OH, creates a more stable carbocation, which is the tertiary carbocation. And the reaction follows SN1 mechanism. So that is why this CO bond is getting cleaved. Okay. So if I break this bond, it will lead to the formation of CH3 plus, which is called as methyl carbocation. This is called as methyl carbocation. But if I break this bond, what I will get? I will get CH3, 3 CH3 I have, right? So it is CH3 3 times and C. So what is this? This is a tertiary carbocation. This is a tertiary carbocation. So which carbocation is more stable? Tertiary carbocation is more stable towards SN1 reaction. So for the formation of this tertiary carbocation, this bond is getting cleaved and the nucleophile H plus I minus is the nucleophile, right? So that nucleophile is coming and attacking this tertiary carbocation, leading to this product. Can you all able to understand? So this is very important. If you have a methyl or ethyl as your alkyl group in the ether, then there is no issue. But if you're having a tertiary group, then the halide part has to go to the tertiary carbon and the hydrogen has to go to the other alkyl group. Okay, because the tertiary carbocation which is formed at one of the step is highly stable in nature, and the nucleophile can come and attack the tertiary carbocation more easily since the reaction is following the SN1 mechanism. Clear for all of you? Do you have any doubt from here? Shall we go for the next reaction? This is the reaction with HX. This is the reaction with HX. Shall we go for the next reaction? Do you have any doubt? Students, I'm waiting for your response. So say yes or no. Am I audible? Anusha, Bhagat, am I audible? Okay. Okay. Okay, thank you guys for your response. So now let's enter into the second type of reaction, okay, which is called as halogenation. So instead of telling this as a second type of reaction, the main topic that I have to give for the second type of reaction is electrophilic substitution reaction. Okay, first we have studied about the reaction with HX, and this is the electrophilic substitution reaction. And under electrophilic substitution, we have 5 types, right? You all know. And the first type is called as halogenation. And that is what we are going to do. Okay, we are going to take an aromatic ether and we are going to do the halogenation, nitration, Friedel-Crafts alkylation, acylation, etc. Okay, so first let me start with halogenation. So what is the name of an aromatic ether? What is the name of an aromatic ether? The very simplest example for aromatic ether is C6H5OCH3, right? What is the name of this compound? Can anyone give me the name of this compound? Can anyone give me the name of this compound? IUPAC name or the common name of this compound? None of you know the answer? Okay, finally I got the answer from Bhagat. Very good. It is methoxybenzene. It is called as methoxybenzene or it is called as anisole. Very good, very good. It is not acetophenone, my dear Jabron. It is not acetophenone. It is methoxybenzene or you can call this as anisole. Okay. So this anisole undergoes bromination. The halogen that I am going to take here is the bromine. Okay. With bromine and ethanoic acid, even in the absence of iron bromide as a catalyst due to activation of benzene ring by methoxy group. Listen. So take the anisole. Take the anisole. Treat it with the electrophilic reagent. So the electrophilic reagent here I am going to use is bromine in presence of ethanoic acid. Ethanoic acid is a solvent and bromine is the halogen part. Here you don't have to use any catalyst, iron 3 bromide or AlCl3, FeBr3. So that kind of catalyst you don't have to use because in the absence of catalyst itself, the reaction will happen. Okay, so this reagent will lead to the formation of Br plus and that Br plus will go to the para position and the ortho position. Okay, so why it is going to para position and ortho position? Why the electrophile is going to para position and ortho position? Because the group which is attached to the phenyl ring is an electron donating group. Okay, it is an electron donating group. So if an electron donating group is attached to the ring, the incoming electrophile will go to the ortho position and para position. Okay, so that is what we have studied for phenols also, right? In phenol also, yeah, in phenol also we had OH. OH group is also an electron donating group. So the electrophile, all the electrophiles which we have studied have gone to the ortho and para. They are ortho para directing groups. Yes, very good, Jabrun. So, but even the two products are formed, only one is the major product. Okay, para isomer is obtained in the 90% yield. Okay, para isomer is the major product. Now, this is the first one. The second electrophilic substitution reaction is Friedel-Crafts alkylation. So here, alkyl groups are formed as an electrophile. Okay, and they are also introduced at ortho and para position by the reaction with alkyl halide in the presence of anhydrous aluminium chloride. Okay, anhydrous aluminium chloride is a catalyst. So take the anisole, use an alkyl halide. So here I have taken methyl halide, methyl chloride. In presence of anhydrous aluminium chloride and carbon disulfide as a solvent, I will get CH3 plus as an electrophile because that is the alkyl part, right? CH3 plus. So that CH3 will go to ortho position and para position. Okay. So para will be the major product. All right. Now going ahead with the next reaction, which is called as Friedel-Crafts acylation. Here you have to take the anisole, treat it with acyl chloride. The acyl chloride that I'm going to take is ethanoyl chloride. CH3 C double bond O Cl. We have two carbon, right? So it is ethanoyl chloride in presence of anhydrous AlCl3. So in presence of this, they will produce CH3 C double bond O plus as the electrophile. Okay. So this is the electrophile. Or I can write this as CH3CO plus. Both are correct only. Okay. So this electrophile, the acyl electrophile will go and get substituted in the ortho position and in the para position. Para is the major product. Okay. So you all know what is ortho para, right? Ortho means adjacent, para means opposite. Clear? This is the third electrophilic substitution reaction. We have studied about halogenation, then we have studied about alkylation, now acylation. Now the fourth one is nitration. So for nitration also what we have to do? Take the anisole, treat it with the nitrating mixture. So who is the nitrating mixture? Can anyone give me the nitrating mixture formula? Let me see who remembers the nitrating mixture formula. We are very good. Only HNO3? Only HNO3? For phenol, we have used concentrated HNO3 and diluted HNO3. But yeah, very good, very good. Very good, students. So concentrated HNO3 and H2SO4. Okay, both together is a nitrating mixture. Can anyone give me the electrophile that is generated from this nitrating mixture? Formula for electrophile that is getting generated. Very good, Rohit Mugilan. Rohit Mugilan, where were you for the last few days? Hmm? Yeah. Okay, okay. One more guy is also there, right? From your school. I forgot his name. Okay, I'll come to this later. So first, let's complete this. So NO2 is the... Okay, Harish, you are here. Okay, Rohit Mugilan and Harish, you both... yeah, you both stay back in the class, okay? I want to talk to you at the last. Okay, now let's go ahead. H2SO4 and HNO3. So the NO2 plus is the electrophile. So that electrophile will go to ortho position and para position. Para product is the major product. Clear? So with this, the theory part of the alcohols, phenols and ethers lesson is getting over. Okay. So let's try to solve one question which has two subdivisions from this chemical properties of ethers, and then we will go for the summary of today's class. And after completing that, I have got some previous year's questions for you from this lesson. Okay, so we will do that. All right. So let's go ahead with the question from this chemical properties of ether. We have studied two reactions. One is reaction with HX and the other one is electrophilic substitution. So this question is from this topic. Give the major products that are formed by heating each of the following ethers with HI. So we have two reactants and both of them are going to get react with HI. Okay. So you have to find out the product that is going to form from this reaction. Can anyone find out the product? You cannot able to type the formula for this big compound. Okay, so you don't have to go for it. Just answer the question which I'm going to ask. Okay, so this is an ether. This is an ether where this is one alkyl group for the first one, and this is the another alkyl group. This is the another alkyl group, R and R dash. R and R dash. We have two CO bond. We have two carbon oxygen bond. RO and R dash O bond we have. And it is reacting with HI. Now you tell me whether RO bond will be cleaved or R dash O bond will be cleaved. You guys tell me which bond will get cleaved. RO bond or R dash O bond. Which one? R dash O bond. Very good. Very good, Sunanda Kumari. It is correct. Why? Can you give me the reason for it? R dash bond or R dash O bond will get cleaved and the hydrogen will go to, yeah, very good, very good. It is a tertiary carbocation formation concept, right? So tertiary carbocation will form and iodine will go here and hydrogen will go here. So we will get alcohol. So it will cleave, H will go here and iodine will go here. So we get propanol and the tertiary iodide compound. Okay. Tertiary iodide, 2-iodo, 2-methyl-butane. These are the two products that we obtain. Okay. And the concept that we have to use is the stability of tertiary carbocation. Okay. Now coming to the second reactant. If this reactant is treated with HI, what are the products formed? Tell me. Here also we have two carbon oxygen bond. So this is one carbon oxygen. This is R dash and this is your R group. Okay. So now here for this product, you tell me which bond will be cleaved. RO bond or R dash O bond? Very good. What is the reason? What is the reason? What is the reason for this? Is it because of the tertiary? No, we don't have any tertiary groups here. We have an aromatic ring and the benzyl system. Phenyl and benzyl we have. We don't have any tertiary groups here. RO bond will get cleaved. That is the correct answer. But why? Small chain, no. That is also not the answer. We have discussed this. We have discussed this in the class. Just think of it. Think of it. Very good. Because of the resonance. Yeah. Very good, Shaheen and Sivamani. It is correct. So the carbon, the aryl oxygen bond, this CO bond is strong due to resonance. And it is also highly stable. So we cannot break that aryl oxygen bond. Okay. So the CH2O bond will get cleaved and hydrogen always goes to oxygen and the nucleophile iodine will go to CH2. Okay. So what are the products formed? Benzyl iodide. This is not chloride, it is iodide, okay? Benzyl iodide. And the other one is phenol. So this part is phenol and this is the benzyl iodide. So what is the concept used here? Resonance or the stability of aryl oxygen bond. Okay, because of the stability of aryl oxygen bond, the other bond is getting cleaved and the nucleophile goes to the other carbon. Okay, so this is all for today. Let me summarize the chemical properties. So first of all, ether has reacted with 2 moles of HX and they led to the formation of alcohol and alkyl halide first, and finally we have got one more alkyl halide also. Okay. Then coming to the reactivity order of HX, HI was more reactive compared to HBr and then HCl comes. Okay. Then after completing this, we have entered into the second chemical reaction, which is called as, before that, we have also studied the reaction of HX with the aromatic system, right? So bond breakage will happen here and HX has to get added like this. Then the second reaction is halogenation. The first one is bromination. The second is Friedel-Crafts alkylation. Okay. Here Friedel-Crafts acylation and here nitration. You just have to keep the mixtures, the electrophilic reagent mixtures you have to keep in mind, and the electrophile that is getting generated you have to keep in mind. Rest all others are easy. Okay, everything remains same for all the electrophilic substitution reaction. So with this, we are closing this lesson. Now, let's go ahead with some previous year questions from this concept. So this question looks similar, no? Not similar. It is exactly same. Okay, it is exactly same with the question that we have solved now, right? You see, the question, this is a question from our NCERT book. At the end of the lesson, you may see this question. The same question has been asked in one of the previous year of your competitive exam. Okay. So what is the answer for this question? What is the answer for this question? Option A, B, C, D. Which option is correct? Option B or C? You guys can able to see the options, right? This is option A, this is B, this is C, and this is D. Find out the correct answer. Find out the correct answer. Very good. Option B is the correct answer. Same explanation. You have to break the bond. H and I has to be added like this, so that option B will become the correct answer for this question. Very good. So without wasting much time on this question, let's move ahead with the second. Match list 1 with list 2. So we have the reagents for the preparation, reagents that has been used in the chemical reactions of phenols. And in the list 2, we have the name of the product that is obtained. So match list 1 with list 2. Rukmini, are you sure that option D is the correct answer? Let's wait for others also. Okay, let's wait for others' reply. And then we will discuss this and we will find out whether D is correct or not. Okay. Everybody is going for option D. What about others? What about others? Pushpa, Madhukar Reddy, Jainvi Roing, Valmiki, Bakat, Anusha. What about you guys? Shreya, Sneha? All of you are going for D? Okay. Option D is the correct answer. So what is the name of this reaction? NaOH and CO2 with H plus, leading to the formation of salicylic acid. What is the name of this reaction? Can anyone tell me the name of this reaction? Yeah. Yes, it is Kolb's reaction. And what about the second one? Aqueous NaOH with CHCl3 leading to the formation of salicylaldehyde. Aqueous NaOH and CHCl3 leading to the formation of salicylaldehyde is the Reamer-Tiemann reaction. Yes, Reamer-Tiemann reaction. Very good. Zinc dust leading to the formation of benzene is a reduction reaction, and last one is the oxidation reaction. Very good. So option D is the correct answer. Now coming to the third question, which one of the following reaction sequences incorrect method to prepare phenol? So for the preparation of phenol, we have studied four methods, four reactions we have studied for the preparation of phenol. You have to find out the incorrect method. Which one is incorrect? Has anyone got the answer? Has anyone got the answer for this? Option A? No. It is correct only. Option A is correct because we have prepared phenol from the oleum, right? So do you remember that reaction? I have told you, right? If you treat benzene and oleum, you will get, oleum means H2S2O7, that fuming sulfuric acid. So it is nothing but sulfonation. Okay, so that will lead to the formation of benzene sulfonic acid. And if this benzene sulfonic acid is treated with NaOH and H3O plus, it will lead to the formation of phenol. So it is the correct method of preparation of phenol. So option A is correct only. You have to find out the incorrect. B is incorrect? No. B is not the answer. Listen, aniline. So from aniline also we can prepare. Okay. From aniline also we can prepare if you treat this with NaNO2 HCl, NaNO2 plus HCl. So this is nitrous acid mixture and this will convert the NH2 group to N2Cl group. Okay. Then if you treat it with the water and if you try to heat this, that is with warm water, this N2Cl part will be converted to OH, right? So that is what we have studied. So this is also a preparation of phenol only. So which is the correct answer? Cumene. From cumene also we can prepare, right? Isopropyl benzene. So that is also the preparation. The correct answer is option D. Chlorobenzene treated with NaOH cannot lead to the formation of phenol at standard temperature and pressure condition. You can get phenol using chlorobenzene and NaOH, but only at very high temperature and very high pressure. In the previous lesson, we have discussed this, right? At 623 Kelvin only, you can 623 Kelvin only you can prepare the phenol from chlorobenzene. Okay, at normal temperature, it cannot happen. Got it? Okay, so option D is the incorrect method of preparation of phenol. Let's go for the next. So it is a statement type question. Please study the statement, look into the statement and give me the answer. Has anyone got the answer? What about statement 1? The acidic strength of monosubstituted nitrophenol is higher than phenol because of electron withdrawing group. What do you say about the statement? Is it right? The statement 1 is correct? Yeah, very good. The monosubstituted nitrophenol. So this is phenol. And if I substitute the nitro group in any of the position, let me substitute in ortho group, okay? Ortho position. So, sorry, para position. This is para nitrophenol. And this is normal phenol. So, we all know that NO2 group is an electron withdrawing group. So, if electron withdrawing group is attached to the ring, it will increase the acidity, right? So the monosubstituted nitrophenol is more acidic. So statement 1 is correct. What about statement 2? Orthonitro, metanitro, paranitrophenols will have same acidic strength as they have one nitro group attached to the phenolic ring. Is it true? No. Very good. It is incorrect. All three will not have the same acidic strength value. Okay. Be more acidic. Paranitrophenol will be more acidic. Paranitrophenol will be more acidic than the other two. Okay. All three will not have the same acidic strength. So the second statement is incorrect. So which is the correct option? C. Statement 1 is correct. Statement 2 is incorrect is the correct answer for this question. Okay. Clear? You know why? If the electron withdrawing group is just opposite to the OH, it will pull the electron density more. It will pull the electron density more. Okay. Not only because of symmetrical, it pulls the electron density more from the ring and making the ring electron deficient in nature. So all electron deficient, more electron deficient species are more acidic, right? So paranitrophenol will be more acidic. That electron pulling effect will be more in case of the para compound. But if you take ortho and meta, there is no effect of having nitro group at meta. Okay, this is meta and this is ortho. This is ortho, right? So you know why? OH is an electron donating group. OH is an electron donating group. So let me draw the pi electrons. Let me draw the pi electrons so that you can understand this better. Okay. So listen. So OH is an electron donating group, right? So the lone pair of electron will be shifted here and these electrons will go here. And what will we get? We will get another structure. And in that structure, we will get a double bond here, OH plus, and here we will get a minus sign, right? But if you do the same thing with the ortho, if I shift the electrons like this, what I'm getting? I will get NO2 and here double bond OH and here the negative charge will come and get localized. Okay. So you know what happens? The negative charges getting localized in ortho and para position, not in meta. Okay, it will not get delocalized in meta. So even if you attach this electron withdrawing group in the meta position, it has no effect because the electrons are not getting localized here, delocalized here in this meta position, right? But here in case of orthonitrophenol, you see, it is the negative charge is on the carbon to which the nitro group is attached. So minus means it denotes the electron. Okay. NO2 group means electron withdrawing group. So it will withdraw the electrons from the ring, making the ring electron deficient in nature. Okay. So orthonitrophenol will be more acidic compared to metanitrophenol. So like this, all three phenols will have the different acidic strength. Got it? It was Harish, right? Did you get it? So all electron donating groups are ortho para directing groups. Okay? Clear? So we will do one more question. It is also a statement type question. Statement 1 says that in Lucas test, primary, secondary and tertiary alcohols are distinguished on the basis of their reactivity with concentrated HCl and zinc chloride, which is known as Lucas reagent. Is it true? Can you distinguish primary, secondary and tertiary using Lucas reagent on the basis of their reactivity? Yes, exactly correct. Sivamani is exactly correct. Option statement 1 is correct. We can distinguish between the types of alcohols by their reactivity using the Lucas reagent. What about the statement 2? What about statement 2? Primary alcohols are more reactive and immediately produce turbidity at room temperature. What about the second statement? Statement 2 is wrong. Very good, Shaheen. Statement 2 is incorrect. Why? Why statement 2 is incorrect? Because tertiary alcohols are more reactive. That is what we have studied in the lesson, right? Tertiary alcohols are more reactive and they produce the turbidity immediately. Okay. Primary alcohols are less reactive. They produce the turbidity only if we heat it. They will not produce the turbidity immediately at room temperature. Okay. So statement 2 is incorrect. So option C is the correct answer for this question. Okay. Option C is the correct answer for this question. Okay. So I hope it is very useful for all of you. It is already time. You guys have joined late, so I cannot able to do more questions for you. So please try to join on time. I hope you guys have the timetable with you. So please look into the timetable and join the class accordingly. Okay, so that we can discuss more questions and we can discuss more concepts in the class. Okay, so do you have any doubts from today's session? Do you have any doubts from today's session? No? Okay. So today we are closing this topic and in the next class, we will start with the new lesson. Okay. We will start with aldehydes, ketones and carboxylic acids. Okay. Which lesson you guys want? Aldehydes, ketones or we will go with amines? Not amines, biomolecules. Which lesson you want me to start? Amines you want me to start? Okay. Only if you understand the aldehydes, ketones, and carboxylic acid, the other two lessons will be easy for you. I can start amines, no issues with amines, but there will be some concepts in biomolecules from aldehydes lesson. So I will think of it and I will start. Okay, whether to start aldehydes or amines. Let me discuss and I will let you know. You guys want amines? Okay, I will tell. Okay, students. So thank you so much for attending the class. I have launched a poll. You guys can give your answers over there and then you can get ready for your next class. Thank you so much. Thank you.